Welcome to Chapter 7, Periodic Properties of the Elements. The elements in the same group generally have similar chemical properties. Properties are not identical, however. One of the main reasons elements in the same group generally have similar chemical properties is because the elements have the same outer electron configuration, and thus all of Chapter 6, and why we describe where the elements probably are. Dmitry Mendeleev and Lothar Meyer independently came to the same conclusion about how the elements should be grouped on the periodic table. And you can see here on this representation the approximate time when these elements were discovered and therefore added to the periodic table. For instance, Mendeleev predicted the discovery of germanium as an element with an atomic weight between that of zinc and arsenic, but with chemical properties similar to those as silicon. And if you look at the periodic table, here's the element germanium, and you can see that it's between gallium and arsenic, and between silicon and tin. And he predicted that the properties would be right between there. And since it's called the periodic table, it turned out that it was fairly similar. In this chapter, we'll rationalize observed trends on the periodic table in terms of sizes of atoms and ions, ionization energy, and electron affinity. We'll talk about why these trends take place, and you, as a student, need to not only know and memorize what those trends are, but you have to be able to explain why the trends happen. Most importantly, of all things, know why these trends occur. First and foremost, before we can rationalize the trends, we need to talk about a basic concept that actually governs almost all of the trends on the periodic table. This basic premise is called effective nuclear charge. In an atom with more than one electron, electrons are both attracted to the nucleus and repelled by other electrons. You can see the nucleus has a positive charge right here. These electrons are attracted to the nucleus, but they are also repelled by each other. Each electron sees or is attracted to an individual proton inside the nucleus. And you can think of it as like a one-to-one electron to proton attraction. The problem is that not every electron has a clear view or a clear look to be attracted to a proton. Sometimes there are electrons in the way. The nuclear charge that an electron experiences depends on both factors, whether they're repelled by electrons and whether they're attracted by various neutrons. The effective nuclear charge is symbolized by the letter Z with a little EFF. And there's actually a mathematical equation there that you can find that. Generally, though, we can say that the effective nuclear charge is equal to the number of equal to the number of protons, and therefore, if there are 11 electrons, there's 11 protons, and so each electron sees a proton. But as I said before, there's a problem with that. Because this electron that's further away from the nucleus might not clearly see the proton that's in the nucleus because it's shielded by all these electrons around the outside. That throws a monkey into the wrench. No, a monkey wrench. Into the electrons seeing a one-to-one effective nuclear charge all the time. Keep that in mind. That more protons, more effective nuclear charge. Further away, though, that the electron is, the less the effective nuclear charge might be, a one-to-one ratio. Okay, that concept behind us. Now we're going to take a look at three different trends on the periodic table. The first being the size of an atom. Size of an atom is defined as the atomic radius, which is 1/2 the distance between two covalently bonded nuclei. You can see right here. Here's the distance between two nuclei. Find half of it, and it's known as the bonded atomic radius. Bonding atomic radius tends to decrease from left to right across the row due to the increasing effective nuclear charge, and increase from top to bottom of a column. Increase from top to bottom of a column due to the increasing value of the principal quantum number. So you can see here that atomic radius increases as you go down, and it increases as you go to the left on a particular period. It's because there's less protons over here in K than there are in krypton, and both have the same number of or the same levels of electrons around there, around the nucleus. Well, what about ions? Ions, remember, are things that gained or lost electrons. So if you look at group 1, for example, they usually want to lose an electron and become a positively charged ion. When they lose an electron, they become smaller. Makes sense. You lose an electron, you get smaller. If you look at negative ions, like oxygen and fluorine, for example, those over in group 6 and 7A, ones way on the right-hand side of the periodic table, generally want to gain electrons. And when you gain electrons, you get bigger. It makes sense. So the general rule is if you gain an electron, you get bigger. If you lose an electron, you get smaller. Atomic size depends on the nuclear charge, the number of electrons, and the orbitals in which the electrons reside. Cations are smaller than their parent atoms. The outermost electron is removed and the repulsions are reduced. Anions are larger than their parent atoms because electrons are added and the electron repulsions are increased. Ions increase in size as you go down a column due to the increasing value of the principal quantum number, or the values of n, which gives you more shells of electrons. And in an isoelectronic series, ions have the same number of electrons. Ion size decreases with an increasing nuclear charge. And so, going back to this term once again, iso, meaning same number of electrons, the size decreases as the nuclear charge increases. So if you look at it from lithium over to fluorine, and if you look on your periodic table, you'll notice fluorine has more protons than does lithium. And so you can see that the atomic size of the ions right here for oxygen and fluorine gets a little bit smaller than oxygen because it has more protons in the nucleus. Lithium to boron as an ion, you'll notice, decreases because boron right here has a few more protons in the nucleus. Second trend to rationalize besides size is something called ionization energy. Ionization energy is defined as the energy required to remove an electron from the ground state of a gaseous atom or ion. Notice it said gaseous, and notice it said ground state. The first ionization energy is the energy required to remove the first electron. Second ionization energy is the energy required to remove the second electron. It requires more energy to remove each successive electron. When all valence electrons have been removed, the ionization energy takes a quantum leap. Back up here a second. They used this term, valence electrons. Valence electrons are the s and the p orbital electrons of the highest energy level. So they're the ones furthest away from the nucleus. Furthest away from the nucleus. Once you remove all those valence electrons, you now have a noble gas configuration. And once you have that noble gas configuration, the atom does not want to lose electrons anymore, and it takes a lot of energy in which to remove it. These I's right here, I1, I2, I3, I4, stand for ionization energy 1, removing one electron. Ionization energy 2, removing a second electron. Ionization energy 3, removing a third electron, etc., etc., etc. And you can see here, just going across a period 3, going from sodium, magnesium, aluminum, silicon, you can see that it takes a quantum jump right here from first to second ionization energy, because after you remove one electron from sodium, it now looks like the noble gas neon. Once you remove 2 electrons from magnesium, then it also looks like the atomic, the noble gas neon, and therefore it has a huge ionization energy. Look at sulfur, same kind of thing. Once it gets to its 7th ionization energy, it will all of a sudden look like neon. General trend is that as one goes down a column, less energy is required to remove the first electron. For atoms of the same group, the effective nuclear charge is essentially the same, but the valence electrons are farther from the nucleus. And so you can see that as you move down this group right here, the noble gases, it's easier to remove electrons from xenon than it is from helium, because the electrons are further away from the nucleus in the xenon than they are from the helium. Generally, as one goes across the row, it's harder to remove an electron. As you go from left to right, the effective nuclear charge increases. And so it's harder to remove an electron from neon than it is from lithium, because neon has way more protons in its nucleus than lithium does. But there are two apparent discontinuities in this trend, and they're circled here on this graph. Notice how the trend is generally upward, but there's some jagged lines in here. Some jagged lines in here. Some jagged lines in here. What are those? The first occurs between groups 2A and 3A. And so it occurs between, in the second period anyway, between beryllium and boron. In the third period it occurs between magnesium and aluminum. That's right here on this little graph. Right here on this little graph. Why does that happen? Because an electron removed from the p orbital rather than the s orbital is a lot easier to do, because the electron is farther away from the nucleus and there's only a small amount of repulsion by the s electrons. And so it's easier to remove an electron from an element, say for instance boron, than from beryllium, because boron's outer shell most electron right here, this element right here, is in the 2p orbital. Here, this one right here is actually the element aluminum, and its most outer shell electron is in the 3p orbital, and it's more difficult to remove one from magnesium right here because it has a full 3s orbital. Same discontinuity occurs here. The second occurs between groups 5 and 6a, and so in this case, in the second period, it occurs between nitrogen and oxygen, and here it occurs between phosphorus and sulfur. This is because nitrogen element right here has a half-filled sublevel. The 2p orbital would have 3 unpaired electrons, 1 in each orbital. The oxygen now has 1 extra electron paired up, and it gets lots of extra repulsion from the other electrons. Down here, the same thing occurs between phosphorus and sulfur. And so it's easier to remove that 1 electron from sulfur than it is from the half-filled p orbital of phosphorus. Last trend to rationalize is something called electron affinity. Electron affinity is the energy change accompanying the addition of electron to a gaseous atom. Notice both ionization energy and electron affinity dealt with the gaseous atom, and they both dealt with the energy change, which is, in our terms, since we studied chapter 5 already, the enthalpy change, either the gain or loss of energy. In the case of electron affinity, lots of times it's negative because it's energy that's released when it gains an electron. In general, the electron affinity becomes more exothermic as you go from left to right across a row. Notice from lithium over to fluorine here, as you gained an electron, generally more energy was given off. More energy, weird discontinuity, more energy is given off. You can see that it kind of generally increases. Generally becomes more exothermic. Remember, exothermic means negative. Once again, there are 2 discontinuities, and the discontinuities happen to be almost in the same place. Notice these are positive enthalpies right here. These, well, aren't very, this one's positive, and then these are, not nearly as exothermic. And the reason for that, again, is the same electron configuration problems that we talked about with ionization energy. The first pair happens between these two groups, and an electron would have to be added into the p orbital here for beryllium or magnesium or calcium. The electron is further away from the nucleus and it feels the repulsion from the s orbital, so it's harder to add an electron to it. The second happens between group 4a and 5a, and they have no empty orbitals here. No empty orbitals right here. Remember, they all have 1 electron in their orbital, and so the extra electron must go into an occupied orbital, creating more electron repulsion. Now let's take a look at some other properties on the periodic table and how they relate to one another. First of all, the property of metals, nonmetals, and metalloids. Metals are on the left side of the periodic table, left of this staircase right here. Nonmetals are on the right-hand side of the periodic table, and they're in kind of a lightish bluish-green color. The metalloids border this stair step. And notice that aluminum is a metal, even though it borders the stair step. It is an exception, polonium as well. The only metalloids really are boron, silicon, germanium, arsenic, antimony, tellurium, and I believe that's astatine. Oh, one more thing. Notice that metallic character increased as you go to the left on the periodic table and as you go down. So where's the most metallic elements? Down here in the lower left-hand corner. Why is that important? Well, here's properties of metals versus nonmetals. And things that are more metallic have more of these properties than others. They're shiny, they're lustrous. Solids, they're malleable, they're ductile. Malleable means you can hammer them into really thin sheets. Ductile means you can draw them into wires. They're good conductors of heat and electricity because they've got lots of free electrons. Most metal oxides are ionic solids that are basic, and they tend to form cations in basic solution. Cations in solution. Nonmetals don't have luster. In other words, they're not very shiny. They're usually brittle, and some are soft. They're poor conductors of heat and electricity, and most nonmetal oxides form acidic solutions. They tend to form anions or oxyanions in aqueous solution. You should memorize those differences between metals and nonmetals. Metals tend to form cations, nonmetals tend to form anions. And you can see right here some common charges for cations, some common charges for anions. Metals tend to be lustrous, malleable, ductile, and good conductors of heat and electricity. Compounds formed between metals and nonmetals tend to be ionic. In other words, there's not very much sharing of electrons in those substances. Metal oxides tend to be basic. Nonmetals are dull, brittle substances that are poor conductors of heat and electricity. They tend to gain electrons in reactions with metals to acquire noble gas configurations of electrons. Nonmetals are substances containing only nonmetals. Substances that containing only nonmetals are called molecular compounds. This is carbon dioxide, CO2, right here in its solid form. Some metalloids have characteristics of metals, some have characteristics of nonmetals. For example, silicon looks shiny, but it's brittle and a fairly poor conductor. They call it a semiconductor. Let's take a look at a few group trends. First of all, the alkali metals, or group 1 metals, are soft metallic solids. Notice they're cutting this metal with a knife right here. They're found only as compounds in nature. They have low densities and low melting points. They also have low ionization energies because their electrons are held fairly loosely. They're the only electron in their highest energy level. Alkali metals have famously exothermic reaction with water because they create hydrogen gas by displacing the hydrogen in the water and therefore causing it to ignite and explode because it creates a lot of heat. Alkali metals, except for lithium, react with oxygen to form peroxides, and rubidium, potassium, and cesium also form these things called superoxides, where oxygen goes from a 0 oxidation number to a 1/2 oxidation number, one of the strangest oxidation numbers you will see. They all produce bright colors when placed in a flame. Here's lithium, here's sodium, and here is potassium with their characteristic flame test colors. Alkali earth metals have higher densities and higher melting points than alkali metals. They also have low ionization energies, but not as low as alkali metals. Calcium, strontium, and barium in their metallic form can react with water, but not beryllium or magnesium. The others readily react with water, as I just said. Reactivity tends to increase as you go down a group because the electrons become further away from the nucleus. Group 6, let's talk about the oxygen group. Oxygen, sulfur, and selenium are nonmetals, whereas tellurium is a metalloid and reactive polonium is a metal. Notice how you go as a transition from pure nonmetal guys, oxygens, to one that's a metal, polonium. Oxygen has 2 allotropes, O2 and O3, also known as ozone. Forms 3 anions, the oxide ion, which is what it is 99% of the time, and then peroxide, which is O2 minus 2, and then superoxide, which is O2 minus 1, which you never see again. It tends to take electrons from other elements, and therefore it gains electrons for the most part. It is a good oxidizing agent. That's where the name comes from. Sulfur is a weaker oxidizing agent than oxygen. It generally exists in a ring form like this. Its most stable allotrope is this S8 ringed molecule. Halogens, fluorine, chlorine, bromine, and iodine are the prototypical nonmetals. Prototypical nonmetals, meaning they want to gain electrons. They have large negative electron affinities. They give off lots of energy when they gain electrons. Therefore, they tend to oxidize other elements easily. They react directly with metals to form metal halides. And chlorine is added to water supplies to serve as a disinfectant. It's a good thing to go around and destroy other molecules because it is a good gainer of electrons. Lastly, group 8, the noble gases. They have astronomical ionization energies because they don't want to lose electrons. They have a noble gas configuration already, and having a noble gas configuration of electrons makes them very, very stable. They have positive electron affinities. Therefore, they're relatively unreactive, and they don't react with very much of anything. Until you get way down here at the bottom with xenon and krypton, every once in a while they'll react with something. They're monatomic gases. They don't pair up. Xenon forms only 3 compounds, and krypton only forms 1 stable compound, and HARF was created in the year 2000. Those are a bunch of periodic properties of the elements. Good luck with your problems on periodicity and periodic trends.